on work done by Christopher Longuet-Higgins in quantum chemistry. He has a degree in physics and a master's degree in history and philosophy science, both from the Faculty of Science of the University of Lisbon. His master's thesis was on the history of boron hydrides. It was entitled Under the Carbon Spell, Diborane's Crystal Structure and the Emergence of Boron Chemistry. So following on that, I'm sure his talk today, Under the Carbon Spell, Aspects of the History of Boron Hydrides from 1916 to 1941.
Thank you all for being present. I will talk about the history of boron hydrides. Boron hydrides, also called boron, are two bonds of boron and hydrogen. They are very reactive towards oxygen, the reason why there are no boron hydrides in nature. They are also very sensitive to moisture and highly volatile. Diborane is the simplest of the hydrides of boron. Modern boron chemistry was founded by Alfred Stock. In 1900, when he was still an assistant to Emil Fischer in Berlin, Stock was holding to an essential analogy between carbon and boron, next measures in the periodic chart, to dream with the creation of a whole new boron chemistry based on the hydrides of boron as rich and flexible as organic chemistry. In order to master the technical difficulties of such challenging compounds, Stock developed new web apparatus whose assembly embodied a new technique that allowed him to deal with all the necessary operations to produce and study the boron's physical and chemical characteristics in a perfectly closed and isolated environment. This would soon become known as Stock's high vacuum technique and was readily adopted inside and outside Germany. Since his first investigation, Stock was immediately able to dismiss all prior investigations due to the pervasive contamination of silicon hydride. In 1912, Stock reported the discovery of tetraborane. 1 year later, he reported the discovery of diborane. By this time, Stock was convinced that he was indeed creating the boron analog of carbon chemistry. In 1923 and 1924, he reported the discovery of the pentaborane, which had no analog in carbon chemistry. At this time, Stock was also submitted the hydrides to an extensive characterization of their chemical behavior. In particular, the hydrides halogenation and their reaction with sodium analogy indicated a clear departure from the analogy with carbon chemistry. Furthermore, Stock's systematic efforts to isolate monoborane, either BH3 or BH4, proved fruitless, and he became convinced of its inexistence. Boron hydrides were beginning to show their unique nature, and Stock was becoming aware of it and slowly departing from his initial straightforward analogy with carbon chemistry. In 1960, with the advent of the Lewis pair of electrons, boranes became electron deficient. That is to say, they did not possess enough electrons to provide 2 electrons in each of their bonds, whatever that structure might be. This is the situation for ethane. It's quite simple, straightforward, but the situation for diborane was not that clear. Throughout the 20s, a multitude of different structures were proposed to solve the problem. The set of all these structures constitutes a surprisingly diverse one, in scope, in aim, and in chemical bond ontology. Most people involved in bond theory were fully aware of the problem and tried to solve it. This was perceived as a pressing problem, and boron hydrides would eventually become the ultimate test to any bond theory. Then there can be no history of bond theory without due consideration for the history of boron hydrides. These are some of the structures. Important, I have no time to address them, but I just wanted you to see how different and how delightful strange some of them seem to be. Diborane proved to be particularly ruthless and despite displayed by some of the authors, the solution always involves giving us some basic picture of contemporary bond theory, like the offset rule or the equation pair. The creative freedom displayed by this model built on the limited empirical information gathered by Stock and on the developing stage of the electronic theory of chemical bonds. As the gaps in the theory were increasingly filled and the number of unexplained compounds decreased, boron hydrides emerged as one of the ultimate challenges for bond theory, and expressions like the chemical puzzle or the most puzzling compounds were frequently used to address divergence. By the late 20s, only two of the proposed models were elected as able to explain the empirical data. The one-electron bond SS-like model by Nevil Sidgwick and Linus Pauling, and the ethylene-like model by one of Stock's collaborators, Egon Wiberg. In Pauling's structure, which Stock represents an electron, two of the hydrogen-boron bonds show only one electron, while the rest of the molecule is according to Lowry theory. In Wiberg's structure, there is an ethylene-like negative core with two positive hydrogen ions loosely bonded to the negative core. The ad-hoc nature of the one-electron bond was Pauling's structure major shortcoming, since only the boron would have this type of bond. The ethylene-like model, on the other side, was rather based on what concerned the exact position of the two hydrogen ions and was therefore not easily represented. This was the reason why Stock used both these representations in his book Hydrides of Boron and Silicon, published in 1933. Due to its ability to explain divergence reaction with ammonia, its mechanism had been proposed by Stock. The ethylene-like model did enjoy the recognition of empirical accuracy, even though the general attitude was a very cautious one. Despite acknowledging the empirical accuracy of the ethylene-like model championed by his collaborator Egon Wiberg, Stock was very suspicious of any model and preferred to continue gathering empirical information in order to solve the puzzle. He argued that the hydrides of boron denied the generality of Lowry theory. According to him, contemporary bond theory concepts had been developed to explain carbon chemistry and were simply unsuited to deal with boron chemistry. In 1930, the structural debate led Hermann Schlesinger and his graduate student Anton Berg to enter the field. They worked at the University of Chicago, and their methods were those of analytical chemistry. Their experimental technique was essentially Stock's high-vacuum technique. Their research program was entirely focused on the structural puzzle. They elected the SS-like structure as their working model, but in their first papers they rejected any theory, including Pauling's one-electron bond, for its lack of generality. They believed monoboron DH3 was the hydride structural unit and that divergence was actually a dimmer, despite Stock's failure in isolating DH3. They accordingly devised a research program to investigate the dimerization conditions of divergence, hoping to become able to prevent it. If succeeded, Wiberg theory would have instant death. In an attempt to track the two one-electron bonds, they studied the substitution of divergent hydrogen atoms by methyl groups. They found out that only 4 of divergent 6 hydrogen atoms could be substituted. This led them to conclude that the remaining 2 hydrogen atoms were linked by a different type of bond. Both Wiberg and Pauling's theories could claim this result, but it did show that divergence was quite different from SN, as already pointed out by Stock. Schlesinger and Berg also looked for reactions that would show evidence of the transitory existence of DH3. Later on, they also engaged in the creation and study of new ammonia compounds of divergence in an attempt to test how solid Wiberg's claims really were. In In 1936, Wiberg wrote a rather comprehensive review paper on the subject. In a surprising move, Wiberg now claimed that chemical evidence alone would not solve the problem, thus giving up his stronghold in the ammonia compound of diborane. This was no innocent move though, as Wiberg was now claiming that several recent physical studies of diborane were explained by his theory alone. In particular, the zero electrical dipole moment of diborane and its diamagnetic behavior did seem to endorse Wiberg's structure, since the two unpaired electrons in Pauling theory should imply a paramagnetic behavior of diborane, while the symmetry of his structure should imply a non-zero electric dipole moment. At this point, Wiberg's theory made a significant move forward, and at least one reviewer did declare the case closed. However, this did not last long, as the next year, in 1937, Simon Bauer, working under Pauling at the Polytech, published his electron diffraction study of diborane. Bauer's work represented a huge upgrade in the discussion, both experimental and theoretical. Bauer claimed the definite solution of the puzzle in favor of the Epstein-like model and the unquestionable dismissal of Wiberg's structure. Electron diffraction studies involved two different techniques: the radial distribution method, which was not model dependent and allowed a direct estimate of the interatomic differences in a molecule, and the stochastic method, which involved the a priori assumption of a structural model for which the theoretical diffraction pattern would be computed and then compared with the actual experimental diffraction pattern of the molecule. Through the radial distribution method, Bauer was able to measure the interatomic distances in diborane, which in the case of the two boron atoms was much longer than those of the typical double bond. In fact, they were even longer than the typical distance for a single bond. Also, boron-hydrogen bonds were all equal. Therefore, Bauer claimed that Wiberg's theory was false. One important thing to keep in mind is that because the stochastic method was model-dependent and the debate had long been restricted to carbon-like structures, Bauer only made computations for Pauling and Wiberg's structures. He also compared the experimental patterns of ethane, ethylene, and diborane. Ethane and diborane displayed truly remarkable similarities. Ethylene was quite different. But how about the physical constants of diborane, those on which Wiberg grounded his claims? Bauer used Pauling's resonance and Mulliken's language to get a pretty complex theoretical argument for a homogeneous ethane-like molecule diborane, which would account for its zero dipole moment and diamagnetic behavior. By doing so, Bauer was able to appropriate the very same empirical data invoked by Wiberg. However, he was now in opposition to Schlesinger and Berg's results, indicating that two of the bonds in diborane were of a different type. He also did not explain the ammonia compound of diborane. So Bauer had been able to build a tremendous firewall against the advance of Wiberg's theory, but only to make Wiberg retreat to his classical stronghold, the ammonia compound of diborane. And he was now in frontal opposition to the chemical evidence gathered by Schlesinger and Berg. The puzzle was now getting deeper, and the only way out to Bauer and Schlesinger and Berg was to hold on to their disciplinary commitments. As to Wiberg, he seemed unreachable in his ammonia compound style, but it was then that Schlesinger and Berg came up with a card they were holding back for the last 2 years. Due to their investigations on the transitory existence of monoborane DH3, they were now in a position to dispute Stock's mechanism for the reaction of diborane with ammonia by proposing a new mechanism to it. Of course, they knew their mechanism was speculative, but so was Stock's, and they only needed to be on equal footing to annihilate Gilbert's advantage. There seems to have been active coordination between Bauer and Schrödinger and Berg in the way they timed their publications that year. In 1942, in an extensive review of boron chemistry, Schrödinger and Berg tried to contribute to the debate's closure by proposing that steric hindrance could justify their failure in substituting more than 4 methyl groups in diborane. Anyway, at this point, Schrödinger and Berg were waving a surprising goodbye to the structural debate. They expressed their disbelief in the power of chemical evidence to contribute to the solution and redirected their readers to Bauer's extensive review of the problem that same year, in which he discussed the implications of the physical and spectroscopical data that had been gathered till then, only to maintain his position. Thanks to all the chemical knowledge obtained during the structural quest, in particularly the results obtained with metalloborane, compounds of metals like beryllium or aluminium with borane, Schrödinger and Berg decided to emancipate boron chemistry from the structural debate for the first time ever. Herbert Charles Brown, then Schrödinger's assistant, played a very important role in this development. By this time, Schrödinger and Brown were both in secrecy about their work for the Manhattan Project, in which they used their knowledge of the metalloborane to meet the request of the USA Armed Forces. It was in this context that the reactions that led the hydrides to industrialization were developed by Schrödinger and Brown's team, liberating at last the field from the really raw yellow with which Stock and Schrödinger had been working. And for the first time ever, the hydrides offered actual applications in the pharmaceutical and organic chemistry industries. Until then, they had been purely academic entities investigating only for their theoretical puzzle sake, produced only by Stock and Schrödinger's group, who provided all the samples used by other investigators to make spectroscopic and other physical measures. This is an important aspect of the history of borane. As soon as one physical method was developed, Stock, but also Schrödinger and Berg, actively cooperated to try to obtain evidence that hopefully would solve the problem. The hydrides of boron are a clear case of deep and systematic interaction between chemistry and physics. The history of the hydrides of boron showed how an analogy and a desire for unification with carbon chemistry founded and guided the emergence of this new field of chemistry. It shows that the structural debate was its single driving force until the 40s, and that boron chemistry reached industrialization prior to the closure of the structural debate. It also shows that the analogy with carbon chemistry, while being fruitful enough to develop the field, also restricted the debate on the borane structure, eventually preventing the debate on the presently accepted structure, which had been first proposed in 1921 and only entered the debate in 1940. I'll just show the solution of the puzzle. This is the presently accepted structure for diborane. This is the 3D model. Bridge model. This is tetraborane. And tetraborane is a beautiful structure, quite different from carbon chemistry. And to my knowledge, boron structures still made specialists today due to boron's ability to form in totally unexpected way. So if I have 2 more minutes, I'll just show you that Schrödinger group held the solution in their hands, but this is a story told by Herbert Charles Brown. And he went to Schrödinger proposing the bridge structure, but said I will write Pauling and Mulliken I would like to emphasize that the statement, this is not our view, we should be very careful. So Brown never saw the correspondence, but indeed Schrödinger writes, wrote to Pauling, and this is the letter. Proposes the rich structure for, and he proposes that an unusual type of hydrogen bond is the solution. And this was Pauling. He also gave some technical reasons.
But I'm happy to entertain any questions for Nuno at this time. Please.
Sure, I can. So my first research project, my own dissertation, was on Pauling and his research group in the 1920s and 1930s. So I'm very sympathetic to your argument that no history of bond theory, especially in this era, is complete without the study of boron and boron structure. What I would like to sort of question or suggest, I also completely agree there's the mistakes that come in because they're working with carbon structures with this assumption, especially when doing electron diffraction where they can only measure the lengths and not the angles. So if they start with a carbon structure, they get a carbon structure in the end. What I would suggest though also for Pauling and for Mulliken was important was this analogy with the H2+, the hydrogen molecule ion, which they take from the physicists and convince them that this idea of one electron bonding is valid. This is one of the only places Pauling and Mulliken don't disagree with each other. What fascinates me about the 1941 correspondence from Schlesinger is not that he would get an answer from Pauling that says, yes, stay with the one electron bond, because that's Pauling's own theory. But what fascinates me is actually Mulliken also accepted the Pauling's one electron bond. He did not accept the 3 electron bond, and there's no physical system, no system for physics with the 3 electron bond. But this 1 electron bond, I think because everyone was too focused on this physics example of H2+, which a lot of the early quantum physics worked on. I think this may be another false lead, that when you look at the physics community instead of the chemistry community, they're getting the wrong results.
I included that in my article. And Mulliken vision that the diagram would be fragmented, either a treatment, treatment of diagram, about that Pythagorean is magnetic, as predicted by Lewis, who proposed some structure. Bauer was the only one that Lewis structure consideration in 1937, because he needed to make an homogeneous model that could explain
Any other questions? We have a little time. I'm happy if anybody has any questions for any of the speakers. If not, I want to thank the speakers. I want to thank the Waters Corporation, and I want to thank you for your attendance and attention. So.